All right, let's go ahead and take a look at 4-6. This is just kind of to get you started. We'll get more in depth with this when I come back, but to get you started on it on 4-6, if you open up your book to page 232, this is the related rates section, which I've titled there, so related rates. This is where we're going to use some of the idea of differential equations where we were using dx, like the change in x, where we'll actually be given how some things are changing and we're able to plug in for some of those values and solve and use it in a story problem way, okay, rather than just plugging in dx like we were doing in 4-5. So where we'll be applying it to the story problem, which I know you are excited about. On page 232, there's lots of good examples actually that they have in this. There's those examples they give, starting with 232, example 1, 2, 3, 4. I'm just flipping through. There's 4 really good examples that you can look through. Some of them might need some extra explanation, but they're pretty good. I'll try to do a couple examples from the homework just to give you a different feel, different look. So on 4-6 related rates, what it is any equation involving 2 or more variables that are differentiable functions of time t. Okay, they can be used to find a variety of things. So that's what related rates. They're going to relate different rates together. So 2 or more variables that are differentiable functions of time t. Okay, so on that, I was going to say we could just look at some of the examples in the book, but I'm going to direct you to page 234, related rate problem strategy. And on page 234 there's 6 steps. 1, draw a picture and name the variables. Use t for time. Assume all variables are differentiable functions of t. 2, write down the numerical information. 3, write down what we were asked to find, usually a rate expressed as a derivative. 4, write an equation that relates the variables. Okay, and then 5, differentiate with respect to t. And then 6, evaluate. All right. So let's go ahead, skip through my notes here. Actually, I wonder if... Sorry, I'm just looking at which one I want to do. Let's go to page 238. Let's do this one. 238, number 13. There we go. Number 13. So on number 13, it's the sliding ladder problem. Kind of a standard type of problem. It says a 13-foot ladder is leaning against the house. See figure. They have a figure drawn for you already. When its base starts to slide away. Now, I don't know if you've ever been on a ladder when its base starts to slide. I haven't, but I've always think about it, and it's a bad feeling. So, by the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. We got to find out how fast is the top of the ladder sliding down the wall at that moment. At what rate is the area of the triangle formed by the ladder and the wall of the ground changing at that moment? At what rate is the angle theta between the ladder and the ground changing at that moment? All right, so we have a few things to figure out here. So I'm going to redraw the picture that they have, and you can do the same. It's not a bad idea to redraw this picture. So here is our ground, here's our wall, and then we're going to draw the ladder like this, and then this is going to be theta here, and here's our 13-foot ladder, and then the ladder sliding down. They have the arrow down there, and the base is sliding out, and they have this as a function of x of t, and this as a function of y of t. So this is all right there in their book. You can just copy this down. Right there. So, all right. So that's the picture drawn for us, and we could have probably drawn that picture as well. So what we know is they're asking a couple questions. It says, how fast is the top of the ladder sliding down the wall at the moment? That's why kind of y of t, our y value with respect to some time t, this is sliding down. And then our x value is changing with respect to time t. And then we actually know what how fast it's moving, which is a change in rate, right? 5 feet per second. So we're going to use that idea as well. So step one, we need to assign some variables. So step one here is x equals the distance from the wall to base of ladder. Okay, so it's the distance, okay, the distance from the wall to the base of the ladder. I'll give you a second to write that. That's what x represents. It's the distance from the base of the wall to the base of the ladder. Y is going to represent the height of the top of the ladder. Height of topo ladder. Okay. And then area, A, that's a variable because we're going to have to find that for part B. Area A stands for the area of the triangle formed by ladder, wall, ground. Ladder / wall / ground. Okay, so the area is this area formed by the ladder, the wall, and the ground. Okay, and then theta is the angle between ladder / ground. That's what theta is. Sorry, the paper's moving on me. All right, so those are 4 variables that we're writing down. And so that's step one. Step one, draw a picture, name the variables and the constants. Okay. Now, step 2 is we want to write down numerical information. So step 1, we've gotten our variables and our constants written. Our step 2 is to give numerical value. So what do I know at the instant? Well, okay, by the time the base is 12 feet from the house. So at that instant, the base here is 12 feet from the house. So what do I know at the instant? So at that instant, x is equal to 12 feet. Now it's going to change, right, as time goes on, but at that very instant, x is 12 feet. What I know then, what else do they tell me? They tell me that the base is moving at a rate of 5 feet per second. So this base is moving in this direction along your x-axis at a rate of 5 feet per second. So that is not the height moving down at 5 feet per second. It's actually the base moving at 5 feet per second. So this is a little bit different. We're going to say dx dt. Usually we're used to seeing x as a variable in the bottom, but in this case, it's the change in our horizontal, as the ladder slides, compared to the time, the change in the time. So at that instant, dx dt is equal to 5 feet per second. Okay? So step 3, so now, well, are we done with step 2? I'll tell you we are, because we've named the numerical values. Now 13 is already a constant. The ladder is not changing at all. It's just 13. All right, step 3 then states for us, or not states for us, what are we supposed to do in step 3? I gotta flip back. It says, step 3, you wanna write down what we're asked to find. So what are we asked to find? Well, we're asked to find 3 things. One thing, the first, is how fast is the top of the ladder sliding down at the moment. So I want to now find the change in my y compared to the change in my time. And that'll give me a rate. So I want to find dy dt, because it says how fast is the top of the ladder sliding down the wall. B is, at what rate is the area of the triangle formed by the ladder of the ground changing at the moment? So now I want to find out what is the change in my area with respect to the change in my time. So dA dt is another thing I want to find. And then it says, what rate is the angle changing? I want to find what is d theta. Now, this again it doesn't say find theta. It simply says find out what the rate of theta is changing at. So it's not saying find theta, it says find the changing rate. So there's step 3. I've named what I want to find. Now, part A then, or excuse me, step 4 is write an equation that relates the variables. Well, the issue is I have variables x, I have variable y. Now, when I'm saying the variables, which part am I referring to? I'm referring to A, how fast is the top of the ladder sliding down the wall? So I actually don't necessarily want to include right now the area or theta. I'm just going to be dealing with the x and the y for the height of the ladder going down compared to the base of the ladder going out. So things that I know is the ladder is 13 feet. I know that. I know that at that very instant, this base of the ladder is 12 feet, right? So that base of the ladder is 12 feet. So 12 feet and 13 feet, okay? I don't know what y is, okay? But I could probably find y. But I don't necessarily need to find y. I want to find out what the changing rate is. So, I can write an equation, though, that relates, okay, the idea of this length compared to this length. Now, it's going to be changing, so I can't just say 12 feet, 12 squared plus y squared is equal to 13 squared. Pythagorean theorem, right? I can't do that because 12 squared plus y, what did I just say? 12 squared, the base, plus the height of, y squared is equal to 13 squared. I could find out what that is, right? It would be 5 at that moment. Y would be equal to 5, but that does not tell me what the change in y compared to the change in time. That just tells me what y is, which doesn't help for solving for part A. So I'm going to move this off, and we may pull it back later. What I want to do is I just want to write an equation, not solve for it necessarily, I just want to write an equation. So the equation I'm going to write is x squared plus y squared is equal to 13 squared, which is 169. Now what I know is that's a constant equation. X squared plus y squared is equal to 13 squared. That equation is constant. That's not going to change on me. I mean, not that equation, excuse me. The 169 is not going to change because that's the length of the ladder. The height of the wall and the distance from the wall to the base, those are both changing, but not that. So now that I have an equation that's relating, okay, my variables, we want to differentiate with respect to x. So I go ahead and I say, okay, I've done this. Remember, it's implicit differentiation. So I'm going to say that this is 2x dx dt, because we're differentiating with respect to x, plus 2y dy dt is equal to 0. The derivative of the right-hand side is 0. So we differentiate with respect to t. That's why this is not dx, like the derivative of the base is 1, because it's with respect to t. Whereas before we'd end up with a derivative of 2x times the derivative of the base would just be 1. It's with respect to t here. So now what I can say is I have, well, I already found out that my y value, which is 5, which we were going to find later, but we found it right here. The y value is 5. So I'm going to make a little note, is that at the given moment, I know that x is equal to 12 at that moment, y is equal to 5, and what's the other thing we know? We know dx dt is equal to 5, because they told us that, and I already wrote it down. Dx dt is equal to 5. So I'll let you look at that for a second. So these are things that I know at that moment. X is 12, y is 5, dx dt is 5. So when I look at the equation that I have, I'm looking at unknown x, unknown dx dt, unknown y, unknown dy dt. I have 4 unknowns. I am ultimately, for part A, trying to solve for dy dt, the change in my vertical compared to the change in my time. I need to plug in for y, dx, dt, and x. Isn't that what I have right up here? Y, x, and dx, dt. So I can plug all those in and then just solve for dy dt. So dx dt is 5 plus 2 times 5, and then I don't know my change in y, like that. So this is going to be 5 and 2 are just going to be constants, actually. You could divide both sides by 10, because 2 and 5 is 10, 2 and 5 is 10. Divide everything by 10, you're going to be left with 12 plus dy dt is equal to 0, and therefore dy dt is equal to a negative 12 feet per second. Now, does it make sense that I have a negative, change in my vertical? Well, sure, because the top of the ladder is going which way, up or down? Ladder, top of the ladder is going down, you're going down with it. So that's my dy dt. All right, so that's just part A. We got to part A. Now part B, oh man, I'm getting exhausted. Part B is we want to find what rate is the area of the triangle changing? Well, the area of the triangle, let me just draw it here again. Here's our triangle. This is my x, this is my y. What's the area of a triangle? Well, the area of a triangle, A, is equal to 1/2 xy. Right? Isn't that the area of a triangle? So I've just written an equation that says, oh, I can find out what my area is changing at. Again, that's my goal. What is my area changing at? So when I do that, I can say, okay, I'm going to differentiate this whole thing with respect to t. Therefore, dA dt is equal to constant of 1/2 pulled out, product rule, x dy dt plus y dx dt. I'll give you a second to look at that. Okay, now what I have here is I want to find dA dt. I have 4 unknowns, actually I have 5 total, 1, 2, 3, 4, 5. I want to find dA dt, so I need to be able to plug in for 4 of them, 1, 2, 3, 4. Well, can I plug in for 4 of them? Well, do I know what x is at that given moment? The answer is, hopefully you can look back up in your notes, but I'll put it right here. Remember, x was 12, y was 5, dx dt was 5. Do I know what dy dt is? You bet. Dy dt, sorry I'm moving fast, but dy dt is negative 12. You can look at that, right in your notes. So I can plug in for everything 1/2 and 12. Dy dt was a negative 12, plus y was 5, and then dx dt was going to be 5, like this. And we get negative 144 plus 25 gives me 119, a negative 119, all divided by 2, so a negative 119 over 2. And since it's a changing area, it's feet squared per second. So that area is changing at 119, which is the same thing as if you did it in decimal form, negative 59.5 feet squared per second at that moment. It's changing that fast. Okay, so you're losing 59 feet squared per second. Now, it's going to be bad when the area hits 0, right? Because when the area hits 0, you hit the ground. That's the idea. All right. Last one. Part C. You're going to love these related rates problems. Man. We want to find, what does part C say? The rate at which theta is changing. So here I have the right triangle again. I have theta right here. I have x and I have y. Don't forget, this is conveniently a right triangle. I need to write an equation that deals with theta, y, and x. What do you think I could use? SOHCAHTOA. Oh, excuse me, what? Yes, SOHCAHTOA. All right, so SOHCAHTOA is what we're going to use. We're going to use the TOA part because we don't have the hypotenuse. And, well, we do have the hypotenuse, it's 13, but we don't want that. We want to relate y and x. So we're going to say tangent of theta is equal to y over x. So now I have my variables listed, and I can go ahead and do the derivative. The derivative of tangent theta is secant squared theta, okay, d theta dt. Remember, we have to take the derivative with respect to t. We're not taking dy d theta and then saying that derivative is 1. So we have to take the derivative of the inside with respect to t. That's why we're getting d theta dt is equal to low d high, so derivative of y with respect to t, minus high d low all over low squared. Now, when I look at this problem, the issue is I have 1 unknown, 2 unknowns, 3 unknowns, 4 unknowns, 5 unknowns, 6 unknowns. X and X are the same. So I have 6 unknowns. I need to plug in for 5 of them to be able to find out, okay, what my d theta dt is. So, do I know x? Hopefully you say, yes, we know x, Mr. Ellison, please, please, please. Okay, we know x. What is x? It is 12. What is dy dt? It is negative 12. Y is 5. dx dt is 5. X is 12. Do I know theta? Well, how would I find theta? Well, I could find theta because that's unknown. Theta at the given moment, not what it's changing at the given moment, what is theta? Well, I can easily find what theta is by saying tangent of theta is equal to 5 over 12 because your y value is 5, your x value is 12 at the given moment. Therefore, theta is equal to, okay, 1, well, actually, we could do this as an exact value. Let's use some trigonometry. Since tangent theta is equal to 5 over 12, we know that cosine, because we're going to eventually get to secant squared, cosine theta is equal to 12 over 13, right? Cosine theta is equal to the hypotenuse, or excuse me, the adjacent coa. So ca adjacent over hypotenuse, so 12 over 13, because this is 13 here. So that's what cosine theta is. Now, why do I care what cosine theta is equal to? Well, cosine theta is I care about that because secant squared theta is a relationship of 1 over, right, cosine theta. So therefore, secant squared theta is equal to 1 over cosine squared theta. And I know that 1 over cosine squared theta is, and what's cosine theta? 12 over 13, 1 over 12 over 13 quantity squared. Therefore, I get out an exact value of 169 over 144. So sometimes in the book, you're going to get these exact values. You're like, well, how did they get that? Well, here is our process of getting there. All right, and so we get 169 over 144. You can go back and check that out. So what I know is that secant squared theta is 169 over 144. So I'm going to put that up here, 169 over 144. I'm going to have to draw a line here. And okay, 169 over 144. I don't know d theta dt. I do know x is 12, negative 12, minus 5 times 5, all over 12 squared. And so what I end up with is theta, d theta dt, after you do all the math, should come out to be negative 1, okay, and this is in terms of radians per second. After you do the math on that. Okay, well, that's it. I'm sure you are just enthused and you're just jacked to get started on 4-6. So try to continue that excitement and good luck.